Hi, ladies and gentlemen. In the last classes, we have understood combinational circuits. That is, those circuits do not have any memory. So they are gate-based circuits in which you apply some excitation and you get some response. The only time that it takes to get the response is the propagation delay of gates and nothing more. But there are certain other circuits, those are sequential circuits with memory, and they are synchronized. Synchronized in the sense that the operation is synchronized to a common clock or pulse signal. So they are relatively slower than combinational circuits. So in this video we see about the basics of sequential circuits and a primitive SR latch. So let me start with that presentation. So the speech is organized into your learning outcomes, overview of sequential circuits, then a 1-bit memory or latch, and a 1-bit memory with inputs and its simulation in QUCS and Verilog, then summary of your understanding. So what you will learn in this video, you will learn about sequential circuits, then you will learn about 1-bit memory element or latch, then you will learn to design an SR latch and simulate it in QUCS and Verilog. So sequential circuits are systems that are synchronized to a clock signal or a pulse signal. Such systems do not change state when the input change state. So in sequential circuits, whenever suppose you have an AND gate that is with all inputs connected to 1 and the output is 1. So now suppose if you change one input to a 0, the output changes after one propagation delay. Just after one propagation delay, the output switches to 0. It doesn't wait for any clock cycle or any clock signal or anything. But sequential circuits are not like that. They do not change states even after changes in inputs. It waits for the clock signal. Okay, so at the clock transition only it changes the output. So there is some they are naturally slower than combinational circuits. Every sequential circuit has a storage element, a memory. So a sequential circuit can be considered as a combinational circuit plus memory. Now let us consider a 1-bit memory element. So consider this circuit here. There are two inverters with the input output connected back to the input. You can see that there is some positive feedback in this system. This Q is connected to the input of A2 and Q bar is connected to the input of A1. Now you can see that in combinational circuit there are no feedback loops because it does not depend on any previous states. But here it is not the case. There is a feedback from input from output to input. So let us assume that this Q equal to 0. Okay, so what happens is this is coupled to the input of A2, so Q bar becomes a 1, and this comes at the input of A1, so that this is 1, so Q remains at 0. Now you can see that Q remains at that state 1 and Q bar remains at 0. Okay, so that way you can store a 1 or a 0 in the system. Now you can see that always Q and Q bar are complement. Suppose this Q is a 1, then this Q bar becomes a 0 and Q remains at 1. Okay, so you can see that Q and Q bar are complements. So the value of Q remains stored in the circuit. Now this simple 1-bit latch stores 1 bit, but we cannot give any input to this. So we will modify it slightly, giving some input to this latch. Now let us look at this circuit. Now I have added an inverter and apply an input here. Here also I add an inverter and apply another input R. So this is a S input and R is input. This S stands for set and R stands for reset. Okay, this is a primitive SR latch with the inputs. Now when now consider the cases when S equal to 0 and R equal to 1. When S equal to 0 and R equal to 1, the set input is a 0 and the reset input is a 1. So since S is a 0, this output of the inverter becomes a high, output of this inverter is a low. When you are this 0 is applied to a NAND gate, so whenever one of the inputs to a NAND is a 0, the output goes high. So irrespective of this input, this output goes high. Now this high is coupled here, the other input is high, so it is 1 and 1 complement. Q becomes a 0. Okay, Q becomes a 0. That is the second line of this truth table. When S equal to 0 and R equal to 1, Q is a 0 and Q bar is a 1. Okay, So I will say that again, when S equal to 0 and R equal to 1, this output, this inverter output becomes a 1 and this becomes a 0. When one of the input to an AND is a 0, the output goes high. So when this is 0, this output goes high. So this high is coupled here, so that there is already, this input is 1, so 1 and 1 complement Q becomes a 0. So this 0 comes here, this output remains at low. Okay, so Q is 0 and Q bar equal to 1. That is a condition for S equal to 0 and R equal to 1. S equal to 0 and R equal to 1. Now we can say that the latch is reset, because the reset input is high. When the reset input is high, the Q becomes a 0. This is the Q output becomes a 0. I can say that the latch is reset. Now let us look at the third line, the condition S equal to 1, R equal to 0. S equal to 1 and R equal to 0. So this output becomes a 0 and this output becomes a 1. So since this is a 0, Q becomes a 1. Irrespective of the other input, Q becomes a 1. And this is coupled here, and 1 complement this Q bar becomes a 0. So Q is a 1 and Q bar is a 0. That is second line. You can say that the flip-flop is set to 1. I'm sorry, the latch is set to 1, 1 0 1 0. Okay, S equal to 1, S equal to 1, R equal to 0, and Q equal to 1 and Q bar equal to 0. Now what if these inputs S and R are 1s? Then what will happen? There's an undesirable condition here, because the outputs of both inverters goes low. Outputs of both inverters go low. So then outputs of both of these NANDs tend to go high. This input is low, Q tends to be high. This input is low, Q bar tends to be high. Both Q and Q bar tends to be high, which is illegal. So that output will be indeterminate state. So that's why I mark XX here in the truth table as a XX, because that output is indeterminate. Now we haven't discussed this case, S equal to 0, R equal to 0. When S equal to 0, R equal to 0, what happens is these input outputs are both high. Outputs of both inverters are high. So what will happen if this is 1? This output will be, output of this NAND will be Q bar and 1 whole complement, that's a Q. And this output will be Q and 1 whole complement, that's a Q bar. Now what happens is it remains in the previous state. There is no change in output. Whatever signal was there in Q and Q bar, that stays there. That is that it remembers the previous state. With S equal to 0, R equal to 0, this latch remembers the previous state. So this is how this truth table look like. When it is S equal to 0, R equal to 0, it remains in the previous state. Whatever state was there, it remains so. It remains in that state. When S equal to 0, R equal to 1, the latch is reset. The latch is reset with Q equal to 0 and Q bar equal to 1. With S equal to 1, R equal to 0, the latch is set to 1, Q bar equal to 0. At 1, 1, what happens is the latch is in an indeterminate state, in a forbidden state. Now let us look at the QUCS simulation for this. Now you can see that this is my latch. The inputs are S and R inputs are given to some signals, okay, and a digital simulation is dropped with a Verilog model. Now I can run the simulation and observe the output. Now you can see that when it is 1 1, when the inputs are 1 1, both tend to be high. It's an indeterminate or illegal case. And when S equal to 1, R equal to 0, the output Q equal to 1 and Q bar equal to 0. This is a set condition. And when it is 0 1, Q equal to 0 and Q bar equal to 1, that's a reset condition. And when it is 0 0, you can see that it remembers the previous state. Earlier it was in 0 1, so it remains in 0 1. Because this is a remembering previous state. 0 0 is a previous state. So previous state was 0 1, so it remains in 0 1. And again 1 1 comes, it is an illegal state. 1 0 comes, again it's a set condition. 0 1 comes, it's a reset condition. And 0 0 again it's a previous state. Previous state was 0 1. So when 0 0 is applied, it remains in the previous state. And this is waveforms for that, just a representation of this truth table. Now let us look at the Verilog model for this. Now we can create a Verilog model for the SR latch. I start with some module with some name SR latch and output wire Q and Q bar. I have two outputs and two inputs S and R. They are both wires. And I have some internal nets S bar and R bar. They are wires S bar and R bar. Now this is the first set of inverters because S is inverter to get S bar and R is inverter to get R bar. And then the last final the NAND gets at the end. NAND N3, its output is Q, its input are S bar and Q bar. And the second NAND gate output is Q bar with inputs R bar and Q, then N module. Now we will run this code and appreciate. I can say I Verilog. You can see these codes. Now I have this SR latch. This is my module, and I have written a test bench here SR latch TB. Here I include my SR latch.v and I write a module test bench with S and R inputs are kept as registers and output wires are output Q and Q bar are set as wires. Then I make an instance of the SR latch with some name y1 Q bar SR. Okay, this is a module. I change the earlier codes. Okay, then I initially begin monitor with the Q bar S and R. Okay, then I dump this file to a srlatch.vcd. Then I apply some signals 0 0 0 1 0 0 1 0 0 0 1 1 that way, and I finish this. Now I will run this functions. I Verilog, I say srlatch.v. Okay, then I can say srlatch tb.v minus o a dot out. Now both are compiled, both the device as well as the test bench are run. Now I will say a dot slash a dot out. Now we can say these things with initially at 0 nanosecond everything is in an indeterminate state. When it is S equal to 0 or equal to 0, it is an indeterminate condition. And when S equal to S equal to 0 or equal to 0, it remembers a previous state. With S equal to 0 or equal to 0, it remembers previous state. But previous state is in indeterminate, so that is why both show X and both Q and Q bar as indeterminate. Now let us look at this line. Here it is 0 1. Now the flip-flop, now the latch is reset with Q equal to 0 and Q bar equal to 1. Now then S equal to 0 R equal to 0, in this it remembers the previous state or it remains in the previous state. If previous state was 0 1, it remains in 0 1. And when S equal to 1 R equal to 0, what happens is Q equal to 1 and Q bar equal to 0. That is the set condition. Again, when S equal to 0 R equal to 0, it remembers the previous state. Previous state was 1 0, so 0 0. And when S equal to 1 R equal to 1, both tend to be high, which is an illegal condition. So this is how I test my Verilog module for SR latch. Now let me go back to my presentation. Now what you understood in this video is that you learned about sequential circuits, then you learned about a 1-bit memory element or a latch, then you modified this and made an SR latch. You simulated it in QUCS and Verilog, and that is the end of this presentation. I thank you all.